In this video, we're going to look at another example of solving a first order non-homogeneous recurrence relation. However, with this one, something slightly different is going to happen. So if we look at our recurrence relation here, it's non-homogeneous because of this plus 3 to the power of n, which doesn't have a subscript in it. And the first thing we do is ignore our non-homogeneous part and write out the complementary function, which is the solution of the homogeneous part of our recurrence relation. So I'm going to write CF is equal to, and it's going to be some constant I'm going to call capital A, multiplied by, and if we look at the number in front multiplying our smaller subscript term, which is the un minus 1, we have a 1 in front. Okay, so it's going to be 1 to the power of n. Now this is a little bit different to what we've encountered before, because 1 to the power of anything is just 1. So I don't need to write 1 to the power of n. I could write that as just 1. And if we have a times 1, well, that's just equal to a. So our complementary function is just equal to some constant a that we'll have to determine later on. Now let's move on to our particular function step, where we have to pick our trial function based off our non-homogeneous part in order to find our particular function, which we then need to add on to our complementary function. So our non-homogeneous part is exponential form. So therefore, our trial function for our particular function will also be of an exponential form with the same base. Okay, so it's going to be some constant, which I'll call lowercase a, multiplied, and it's going to be 3 to the power of n, like that. Okay, so that's going to be my trial function for my particular function. Now, my particular function should be a solution of my recurrence relation, so I'm now going to substitute it in to help me find a. So to substitute this into my recurrence relation, let's look at our subscript terms. We've got un, so I can replace that with what's written here. However, the problem is going to be the un minus 1. I need an expression for that. So I'm now going to go to my trial function, and I'm going to replace the n's, which is here and here, with n minus 1. So we would get n minus 1 is equal to a multiplied by 3 to the power of n minus 1, like that. Now what we're going to do is substitute all of this information into my recurrence relation. So let's start with un on the left-hand side. That's going to be a times 3 to the power of n. And then we've got equals to, and then we got our un minus 1, which is this expression here. So a times 3 to the power of n minus 1. And then we got a plus 3 to the power of n, like that. Now, if we look at our left-hand side and look at our right-hand side, the one difference is on the left-hand side, all our powers of 3 are n, whereas on the right-hand side, we have an n minus 1 and an n. Now, I want all those powers to be the same, so given that 2 of them are n, I'm going to try and make the n minus 1 an n. So how do I change a power of n minus 1 into n? Well, I need to increase it by 1. So how am I going to increase the power of this by 1? Well, I'd have to multiply by 3 to the power of 1, because when we multiply with the same bases, we add the powers. So then we would have n minus 1 plus the 1, and that is going to give me n, which is what I want. However, that's going to change the value of the term. We can't just multiply it by 3. So to balance it out, I'm going to go to the number multiplying it, and I'm going to divide it by 3. Because if you're multiplying by 3 and dividing by 3, well, then you're doing nothing. Both of those cancel each other out. So now let's write out my new equation. It's going to be a times 3 to the power of n. And then we're going to have a divided by 3. So I'll write it as a over 3. And then this here is going to be 3 to the power of n, which is what I was trying to get. And then we got the plus 3 to the power of n. Now, one also major difference between my left-hand side and my right-hand side, well, in the left-hand side, the base of 3 only appears once, whereas on my right-hand side, we've got it twice. Okay, so I want to rewrite the right-hand side so it only appears once. So I'm going to factorize out the 3 to the power of n. So I have 3 to the power of n multiplied by a over 3. And then for my other term, well, I've just got one lot of 3 to the power of n there, so it's going to be a plus 1 like that. So now both sides are in the same format. I can clearly see how much 3 to the power of n I have. I have a lots on this side, and I have a over 3 plus 1 lots on this side. Well, the amount of 3 to the power of n I have on both sides should be the same. So I'm now going to equate coefficients. So I would have a is equal to a over 3 plus 1 like that. So now I have an equation that I can solve for a. So I'm going to start by multiplying by 3 to get 3a is equal to a plus 3. then subtract a to get 2a is equal to 3, and therefore if we divide by 2, a is going to be equal to 3 over 2. So what I now can do is go back to my trial function and fill this value in, and I've got my particular function. So if we go up here to my un, that's going to give me my particular function pf, and it's going to be equal to a, which is 3 over 2, multiplied by the 3 to the power of n, like that. Okay, so now I've got my particular function, and I've got my complementary function. So what I'm going to do is I'm going to add them together. Okay, my solution, un, is going to be equal to my complementary function a, plus my particular function up here. So plus 3 over 2 times 3 to the power of n. And that is a general solution for this statement here given in the question. Now we need to find a particular solution. To do that, I have to use my initial condition over here in order to obtain this value of capital A, which is what's making this a general solution. Okay, so u0 is equal to 4. So in this case, n is equal to 0. And then the value of my term un is equal to 4. So I'm going to substitute the 4 in for the un, and in place of the n's, I'm going to put a 0. So I would have 4 is equal to a plus 3 over 2 times, and then it's going to be 3 to the power of our value for n, which is 0. And then we can simplify what we've got there. 4 is equal to a plus, and we got 3 over 2 times 1, because 3 to the power of 0 is 1. So that's going to be 3 over 2. And then if we subtract 3 over 2, we get a is equal to 5 over 2. And then I got my value for a, which I can now put in up here to get my particular solution. So it's going to be un is equal to our value for a, 5 over 2, plus 3 over 2 multiplied by 3 to the power of n. And that would be my particular solution for the whole recurrence relation at the top, including the initial term I'm given.